Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will see some examples on Leibniz theorem in the topic successive differentiation. We know that Leibniz theorem, that is product of nth derivative product of two functions, is yn equal to nc0 unv plus nc1 un minus 1 v1 plus up to dash 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 plus ncr un minus r vr plus up to ncn u vn. You can write this theorem as yn nth derivative yn equal to nc0, and difference of this is n minus 0 is n, base of first function un, and this 0 is base of second function. It is 0 means win, plus nc1, and difference of this is n minus 1 base of first function, and this index 1 is base of second function. Similarly, plus dash 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 plus difference of this is n minus r base of first function and r is base of second function, plus dash 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 ncn, difference of n minus n is 0, that is u0 equal to u, and this index n is base of second function. That means you can write statement of Leibniz theorem easily as yn equal to nc0 unv plus nc1 un minus 1 v1 plus up to dash 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 plus ncr un minus r vr plus dash 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 ncn u vn. Now consider one example. If y equal to sine inverse x, prove that in bracket 1 minus x square bracket complete yn into yn plus 2 minus in bracket 2n plus 1 bracket complete into x yn plus 1 minus n square yn equal to 0. We have to prove this result using Leibniz theorem. Consider solution of this example. We are given that y equal to sine inverse x. Differentiating, we get derivative of y is y1 and derivative of sine inverse x is 1 upon square root of 1 minus x square. After simplifying, multiply this term, take this term in LHS side so that we get y1 into square root of 1 minus x square equal to 1. After squaring, we get y1 square into bracket 1 minus x square bracket complete equal to 1 by squaring. Differentiating this term, we get use product rule 1 minus x square as it is, derivative of y1 square is 2y1 into derivative of y1 is y2 plus y1 square as it is, derivative bracket is minus 2x equal to 0. We can write this term as 1 minus in bracket 1 minus x square into y2 minus xy1 equal to 0 by cancelling 2y1 in each term. Now we use Leibniz theorem to find nth derivative of this function. nc0 unv, take u as y2 and v as 1 minus x square. Since in result we have to find yn plus 2, here 2 is there. After taking nth derivative we will get yn plus 2. So that we have assumed u as y2 and v as 1 minus x square. Using Leibniz theorem we get nc0 unv, that is derivative of y2 and the derivative of y2 is yn plus 2 un v means 1 minus x square as it is, plus nc1 yn plus 1, take one index less than this term, yn plus 1, take derivative of this term, that is minus 2x, plus nc2, take one index less and derivative of this function, second function is minus 2. If we take nc3, then we will get nc3 yn minus 1 and derivative of this function will be 0, and so that this term will be 0. So we have stopped here after taking. If there is constant, then stop taking next term. Minus, now we use Leibniz theorem for product of this function. Now in bracket, here minus sign is there, so we take another bracket, nc0 unv, derivative of y1 is yn plus 1, v means x as it is, plus nc1, take one index common, yn we get, and derivative of x is 1. Here 1 is also constant, so We have stopped here. Bracket complete equal to 0. After simplifying this, NC0 is 1. So that we get 1 minus x square yn plus 2 plus NC1 is n. So that we get here minus n is there. So that we get minus 2nx yn plus 1 plus NC2 is n into bracket n minus 1 upon 2 factorial into minus 2 yn minus NC0 is 1. So that minus xyn plus 1 plus NC1 is n. So that we get minus yn equal to 0. After simplifying we get in bracket 1 minus x square bracket complete yn plus 2 minus, you take yn plus 1 term common, that is xyn plus 1 term common. So that remaining term is 2n plus 1 minus sign is taken common. So that we get in bracket 2n plus 1 bracket complete into xyn plus 1. Here 2 cancels, n square and there is minus sign, so that minus n square, here minus plus nyn and minus nyn cancels. So that finally we get minus n square yn equal to 0. So that finally we get in bracket 1 minus x square bracket complete yn plus 2 minus in bracket 2n plus 1 bracket complete into xyn plus 1 minus n square yn equal to 0, which is required answer. Now we consider another example. Find nth derivative of function y equal to x cube e raised to x. That means if y equal to x cube e raised to x, then find nth derivative of y. That is here product of two functions, that is x cube and e raised to x. We know that Leibniz theorem is yn equal to nc0 un v plus nc1 un minus 1 v1 plus nc2 un minus 2 v2 plus up to ncr un minus r vr plus last step is ncn u v n. So that yn equal to nc0, take e raised to x as u and x cube as v. So that we get nc0, nth derivative of e raised to x is e raised to x, and v means x cube as it is, plus nc1, nth derivative of e raised to n minus 1th derivative of e raised to x is e raised to x, take derivative of x cube is 3x square plus nc2 e raised to x as it is derivative, and derivative of 3x square is 6x plus nc3 derivative of e raised to x as it is, derivative of 6x is 6. So that yn equal to, here nc0 is 1, so that we get yn equal to e raised to x x cube plus nc1 is n, so that we get 3n x e raised to x x square plus nc2 is n into bracket n minus 1 upon 2 factorial e raised to x into 6x plus nc3 is n into bracket n minus 1 into bracket n minus 2 upon 3 factorial e raised to x into 6. So that we get yn equal to e raised to x into x cube plus 3n e raised to x into x square plus 2, here there is 6. After finally simplifying we get 3n into bracket n minus 1 into x e raised to x plus, here 3 factorial is 6, here 6 cancels with each other, so that we get plus n into bracket n minus 1 into n minus 2 e raised to x. Thus, finally we get yn equal to e raised to x into x cube plus 3n e raised to x into x square plus 3n into bracket n minus 1 into x e raised to x plus n into bracket n minus 1 into bracket n minus 2 into e raised to x. Thus, using Leibniz theorem, you can find derivative of nth derivative of any product of two functions. Now consider another example. If y equal to e raised to 10 inverse x, prove that in bracket 1 plus x square yn plus 2 in bracket 1 plus x square bracket complete into yn plus 2 plus in big bracket 2 into bracket n plus 1 bracket complete into x minus 1 big bracket complete into yn plus 1 plus n into bracket n plus 1 bracket complete into yn equal to 0. We have to prove this result. Let us consider the solution of this example. We have given that y equal to e raised to 10 inverse x. Differentiating, we get derivative of y is y1, derivative of e raised to x is e raised to x, that is e raised to 10 inverse x is e raised to 10 inverse x, but derivative of 10 inverse x is 1 upon 1 plus x square. After simplifying, we get take 1 plus x square in LHS side, so that we get in bracket 1 plus x square bracket complete into y1 equal to e raised to 10 inverse x. That is in bracket 1 plus x square bracket complete into y1 equal to y. That is y is e raised to 10 inverse x. Now again we differentiating this step. 1 plus x square as it is, derivative of y1 is y2 plus y1 as it is, derivative bracket is 2x equal to derivative of y is y1. So that we get in bracket 1 plus x square y2 plus 2x minus 1 in bracket complete into y1 equal to 0. Now here there is product of two functions, here there is product of two functions. We use Leibniz theorem, so that for this term 1 plus x square in bracket 1 plus x square is one function, y2 is one function, product of two function, and we use Leibniz theorem for this function, so that we get first bracket. Here there is product of two functions, using Leibniz theorem we get second bracket. For first term 1 in bracket 1 plus x square y2 we use Leibniz theorem, so that we get nc0 unv y derivative of nth derivative of y2 is yn plus 2, v means 1 plus x square as it is, plus nc1 yn plus 1, take one index less, derivative bracket is 2x, plus nc2 one term less, that is we get yn, and derivative of 2x is 2. Here constant term is there, so we stop taking next term. Since if we take nc3, then we will get yn nc3 yn minus 3, and derivative of this term is 0, so that we will get 0. So that we, if there is constant, then we have to stop. Bracket complete. So plus we use now here Leibniz theorem for product of these two functions, nc0 unv derivative, and the derivative of y1 is yn plus 1, v means 2x minus 1 as it is, plus nc1 take one index less, that is we get y1, and derivative of 2x minus 1 is 2. Here constant is there, so we have stopped here taking next term, bracket complete equal to 0. Now we have to simplify this. nc0 is 1, nc1 is n, nc2 is n into bracket n minus 1 upon 2 factorial, so that we get 1 plus in bracket 1 plus x square bracket complete into yn plus 2 plus 2nx yn plus 1 plus nc2 is n into bracket n minus 1 upon 2 factorial 2yn plus nc0 is 1, so that we get in bracket 2x minus 1 bracket complete into yn plus 1 plus 2nyn equal to 0. Now we have to simplify this term, so that we get in bracket 1 plus x square yn plus 2 plus 2nx yn plus 1 plus, here there is yn, here there is yn, 2 cancels each other, we get n square minus n plus 2n, so that we get n square minus n, so that n into bracket n minus 1 yn plus 2x minus 1 yn plus 1 plus 2nyn equal to 0. So after simplifying we get in bracket 1 plus x square bracket complete yn plus 2 plus, we have taken yn plus 1 common, so that we get 2 into bracket n plus 1 x, that is 2nx yn plus 1, and minus 2x minus 1 plus 2x minus 1 yn plus 1 plus, here there is yn, here there is yn. After simplifying we get n into bracket n plus 1 yn, n square minus n plus 2n, that is n square plus n into bracket n plus 1 yn equal to 0. you can find in the derivative of product of two functions. Similarly, you can solve any example. Thank you.